Get on my boy Yang Zhang there and say, hey, you got to start grading these quizzes there, dog. But anyway, because how many quizzes do you all have graded so far?
2. We have 2 graded.
2 graded? And we've done 5? Oh my gosh. All right, so he's got to get on that. All right, I will, I'll do some, what do they call it? Legal rendition or something on him, something like that. All right, yeah. Anyway, extreme rendition or whatever that bizarre Cheney-esque word was for basically torturing people. All right, now, so anyway, but let's start with quiz 6. Okay, let's do quiz 6 here real quick because I want you to get an idea of this. Okay. Now, there's going to be 3 questions. I'm going to write them here on the .cam because this thing is working now. I figured out what was wrong with this. Whenever it doesn't work, it's probably just because the batteries are dead. There we go. All right, now, here comes your first question. Are you ready? You ready? Okay. Okay, question number 1. This is quiz 1. Got an let's say a proton. A proton is, all right, so here's my proton, all right? And let's see, I've got an electric field. Let's do it. So it comes out of the page, that goes that way, okay. All right. Here's my uniform electric field. Okay? Here's what my uniform electric field looks like. So which way is that going? Which way is that uniform electric field coming? Towards you, right. Remember, because this is the point of the arrow coming, of the vector arrow coming right out at you. Okay? So it's coming out at you. Got a proton, and it's going like this. Its velocity, the velocity of the proton is going this way. Give me the direction of the force. Direction of F of B. Give me the direction of the force of B for a proton. Exactly. Oh, wait a minute. Which way is it going? All right, which way is the electric field? Which way is the electric field? Which way is the force going? All right, so which way is the magnetic field coming? Out at you. So take your, almost like turn around. So take your hand, put it like this. So if you're sitting there, the way you guys are sitting, it's going like this. Okay? So you go like this, and then which way? So which guy becomes your proton? Your thumb, right? So which way is the force going? Down. 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 Yeah, but one of my star pupils said up at first, so I went, yeah, it's up. And then it's going, no, it's not. No, it's not. So it's down. It's down because the magnetic field's going this way. It's going like this, so you just curve your fingers down like that, okay? Because this is telling me the magnetic field is coming towards you. Okay, so it's coming towards you. Yeah. There you go. Okay, I think Caitlin's got it now, so we can move on. All right, now question 2. Electron. Direction of F of B. Same situation, but this time I've got an electron going through there. What is the electron going through there? So what is the direction of the force now? It's an electron moving through there. So which way is the direction of the force? Up, right? So you do the right-hand rule for proton, and then if it's an electron, you just go, oh, okay, since the proton will be going down, the electron will be going up. Right. So it'll be going up. Very good. Very, very good. All right. Now, question 3. Write the equation of the force. See if you can remember it. Of magnetic force. See if you can remember what it was. Because we're going to have, by the time we get through chapter 20, you're going to have about, well, I don't want to scare you. Chasey's already looking at me like, how many equations are we going to have? A few, but they'll make sense to you, believe it or not. They'll actually make sense. Okay, so what did that equation look like? Anybody want to take a stab? F equals, okay, Abby's all over it. F equals, then what? QVB, right. F equals QVB. Is that really 100% correct? No. What else we need to add there? The sign, because it's a curling force. It's a curl, okay? That force is a curling force. Sine theta. In other words, in fancier physics, like in physics 460 or something, you'd see this. You'd have Q, but they'd actually probably say J, which means a free charge moving about. And they'd have this. They'd have F cross B, like that. That's what, but we just go, I'll draw the picture and I'll tell you the direction because I'm going to use my right-hand rule. We're not going to use matrix algebra, okay? We don't need it because I think with pictures and with your right hand, you can do anything, okay? All right. Ooh. Ooh. Stop the camera. You guys are terrible. Just terrible. I can't believe that. Shoot. All right. Oh, my. We better move on. Okay. It's almost like class. Oh, you almost made me blush. That's embarrassing. Okay. You missed it? Well, good. We're not going to repeat it. All right, now.
It's on the video, though, right?
Yeah, it's on video. Yeah, it's out there. It's on video. Everything you can do with pictures in the right hand. But anyway, all right, now. Goodness gracious. All right, so now you got me all flummoxed. I can't think of another question. But that's enough. That's basically what we learned yesterday. Oh, let's do one more. Let's do one more. I want you to write the expression. I want you to write the expression for the mass. Write the expression for the mass of an object, of a proton. Now this one you're going to be like, what is he saying? Because I'm making it up on the fly here. Write the mass of a proton. Write the expression mass of a proton in moving at a constant velocity, at a constant speed in a constant electric field, constant magnetic field that's perpendicular. Basically, here's what I'm saying. Here's what I'm saying. All right, here's what we've got. Here's what we've got. We've got this. Let's say we've got a magnetic field that's going into the board. Okay, so we've got a uniform magnetic field going into the board. Now, let's make it an even bigger magnetic field so that, now then, my little proton is moving along right here. Here's my velocity, my proton. So he's going into the board. So which way is his force? Which way is the force he's going to feel? It's going to go up. So what he's going to start to do is he's going to start to turn. But when he starts to turn, guess what? Is his velocity, even though he's turning, is it still perpendicular to that magnetic field? Yeah, sure, because you can go like this, right, and keep your thumb like that. So that's what's going on. All right. So he feels the force up, and then when he gets to this position, let's draw the magnetic field even bigger. So then when he gets to this position right here and he's flying this way, he's still perpendicular. He's still perpendicular, but now he feels the force like this. And then when he gets over here, his velocity is still perpendicular, but he feels the force like this. Okay? All right, so basically, he's going in a circle at a constant speed. And what does the force equal? Because he's always perpendicular, so what's his magnetic force equal? F equals what? You already said it in question 3. QVB, sine theta, but the sine it's 90 degrees. Now, if something is going in a circle at a constant speed, does it also have a force going towards the middle? The centripetal force. What was that expression? Remember? No, don't do that to me. Don't tell me first semester stuff. I did the brain flush. No, you can't do that. All right, now then. Okay, here we go. mv squared over r equals qvb. Now, find out what m is. Do a little algebra. Get your mind right. Let's do a little bit of algebra here. So mv squared over r equals qvb. Do I have any vidiots in here today? Any of my video people take my video class? No vidiots in here today? Oh, couple? I owe you all a huge apology. I've got to grade your exams. They're sitting on my desk. They're staring at me like the money I could be saving at Geico, and I got to get them done. So as soon as this class is over, I'm going to help Greg on his homework, and then we'll get it done. All right. Actually, I got USAA, but that's neither here nor there. All right, now. Okay, did y'all find it? It should be QBR over V, right? Yeah, QBR over V. Good. Okay, good enough. Good enough. That's enough for that. All right. So that, let's do it this way. Let's do it this way. Everyone pass it like down to Jordan and down to Taylor and down to Dennis, I think. Yeah. And then, that way. Pass them down that way, and then you all pass them down to Stacy and then to Greg, and on back to Jeffrey there. And then you all pass them, yeah, whichever way you want to do it. Just kind of pass them down towards the middle so I can pick them up. And then that way when the class is over, you all can vamoose. Okay? You don't have to turn them all in a big, huge pile. But I'm going to get on my boy Yang here and say, Yang, you're asleep on it. Uh-huh. How do you, oh, it'll be given.
It's not in our system that we're one of the questions we're supposed to do.
Oh,
They don't give you
this morning, so it's got some questions. Yeah, I think there's like 11. Oh, and that's the other thing. I've been doing you dirty on your homework. You know, besides mastering physics every once in a while, doing you dirty by saying, no, that's wrong. When you put 9.2 and the actual answer is 9.1, you know, that kind of stuff. But anyway, I haven't been giving you the homework hasn't been of equal value. I had the problems as equal value set up originally. In other words, your first homework assignment was like 15 questions. That was worth like 31% of your grade so far, of your homework grade so far. And then that short one that I just gave you over the circuits was only going to be like 14%. I went, no. I gave you the short assignment to make up for some of those big ones, so I changed it. So each homework assignment is going to have the equal weight regardless of how many questions there are. Oh yeah, and you still get a drop 3. Yeah, still get a drop 3. What does the new assignment do? I think I made the new assignment do a week from Thursday. So that way we'll talk about the problems on Friday. Yeah.
that don't work. So bio test on Thursday, and then we have one the day after.
I can't operate that way. I mean, you got this weekend to get them done, so it'll be all right because we'll finished. We'll be mostly done. All right.
Friday?
Yeah, we'll be done with this chapter on Friday. Easy. We'll be done today. All right. Now, so let's take a look at example 2 here in the book. Now that we know everything, all right, we know the right-hand rule. Oh, here it goes. It says I've got a particle of charge. This is on page 663 of your book. I got a particle of charge Q is equal to negative 5.0 times 10 to the negative 4 coulombs. Okay? 663. We're going to zoom in a little bit. All right. Now then, and it has a mass of 2 times 10 to the negative 9, has a mass of 2 times 10 to the negative 9 kilograms. Okay? All right, now then, it moves at a velocity of 1,000. The velocity is 1.00 times 10 to the third meters per second. And that's in the positive x direction. Okay? Now then, it enters a uniform magnetic field that points in the positive y direction. Okay? So, example 2, 663. Okay, so it enters a magnetic field of 2. I'm going to go ahead and put little vector signs on these of 0.2 Teslas. And that is in the positive y direction. Okay. Now, yes? Can I zoom in some more?
9.2.
Yeah. We'll make it real big. Zoom in. Dang, James Cameron's going to call me. I'm going to do Avatar 2. All right, there we go. 0.2. To the negative 9. To the negative 9 kilograms. I was thinking of charge for some reason. 10 to the negative 9 kilograms. All right. Yeah. So it's a nanogram, right? Wouldn't that be a nanogram? Yeah. That sounds like something you'd send somebody on Valentine's Day. Here's my nanogram. Oh, well. Anyway, so we've got... all right. Now, the question is this. The first question is, what's the direction of the force? Positive x direction is the velocity. Positive y direction is the thing. So which way is the force? If it's going in positive, magnetic field's going straight up. This is coming straight. So it's coming out. Now, the old way we used to teach this, in the your old physics books, it would have said out of the page. But that'd be wrong for this one. Why? No, 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 no. Look, magnetic field's going up. This is going this way. So which way is the force going? Look at the charge. What kind of charge is it? It's a negative charge. So which way is it going to go? It's going to go the opposite way of a positive charge, of a proton. So it's going to go into the board, okay? Which would actually be the positive z-axis, okay? So it goes in the positive. So the force of B is in the positive z-axis. All right, and you can do that with your thing, because this will be x, this will be y, this is z. Okay, that's the positive. This would be, yeah. So this actually goes in the direction of the negative z-axis, right? Goes in the direction of the negative z-axis because I've got a negative charge. Okay, if you're not used to this three-dimensional thing, let me just do a quick explanation here. You usually have the x-axis look positive. Here's positive x. Here's positive y. Here's positive z. Okay, there's a little three-dimensional thing. So, if this is where your thumb's supposed to go and this is where this is supposed to go, then the positive, there we go. It's like this. There. That's kind of, don't take it personal. But anyway, so we've got it like this, right? Now then, so that's the positive z. All right, so now since it's a negative charge, it's going this way because it's got a negative charge. Right, yeah, it looks like, yeah, we're flashing little physics gang signs, right? Okay, going to spray paint E equals MC squared on the side of the building. All right, now, okay, then the next question is this. What is the magnitude of the force on the particle when it's in this field? Notice they didn't want a direction. We've already done the direction part. The magnitude, F of B, will equal QVB. Okay, this is just 5.0 times 10 to the negative 4. Notice it just asked for the magnitude, so I'm just going to give the a positive number here, times 1.0 times 10 to the negative 3 times B, which is 2.0 times 10 to the negative 1. So I can multiply 5, that's 10 to the negative 7. 10 to the negative 8, actually. And what is that? What is that unit? It's a force. So what would the units be? Newtons. Yeah, good old newtons. Right. Force doesn't change. Just because this gets crazy doesn't mean that force changes. All right. Oh, wait, that's not the negative 3. It's a positive 3. Sorry. My bad. There. So that'd be 10 to the negative 2, which equals 0.1 newtons. There. That makes sense. All right. Okay, now the next question is, this is basically where I got your quiz question for the most part. It says, because the magnetic force is the only force acting on the particle, it is also the net force. Oh, so the third part we're supposed to find out is, what is the radius of the circular arc? What's the radius of the circular arc that the particle will travel while it's in the field? In other words, it's going to hit that field. mv squared over r equals qvb. So we've got to find out the radius of the arc. So we've got this. We know that mv squared over r equals qvb. Well, we already found out that qvb is 0.1 newtons. We know that we know what m is, and we know what v is. So it's, well, let's just go ahead and do it this way anyway. This is the way they wanted us to do it. We'll just go r equals, multiply by both sides and divide mv squared over qvb. Sounds like some kind of drugstore. Anyway, all right. And then that cancels, So we get mv over qb. And so that radius, if we plug in our numbers, comes out to be 2 times 10 to the negative 2 meters. Or 0.2 centimeters. All right. Okay, so if you were like taking a multiple choice test question or something like that, all right, and it said that a particle enters is traveling at a velocity that's perpendicular to a magnetic field, okay, and we got 3 particles that are entering it, and they all have the same velocity, but one particle looks like this. Here's particle 1. One particle looks like this. Here's particle 2. And one particle looks like this. Path looks like this. Particle 3. Can you see that? They have the same velocity. Which one has the biggest mass? Which one has the most mass? Now look at this equation right. Look at this equation right here. We got mv over qb. Which one? Oh, they have the same charge too. And they're in the same magnetic field. They got the same charge, but which one's the most massive? 1? What's that? Which one's going to increase? Which one has the biggest radius? 3. So if we look at the radius, if m gets bigger, what's going to happen to the radius in this equation? It's going to get bigger if v and q are the same thing. Okay? All right, now let's say they all have the same mass. Let's say they all have the same mass. Which one has the smallest charge? Look at that equation again.
1.
Which one has the smallest charge? 3. Because it's got the biggest radius. So if we put it in the denominator, if this gets smaller, r gets bigger. Right? So, and that kind of makes sense, because if it has no charge whatsoever, what's it going to do? Just go straight on through there. It's not going to care. You know, it'll just go straight on through. It's not going to curve at all, because it's not magnetic or anything like that. Okay? All right, so kind of keep that in. Oh my gosh. I had 6 more examples to do. We only got through 1 of them. Okay, better go quick. Shouldn't have given you the quiz. No, you actually needed a quiz. All right. Now, okay, so they went ahead and they give a whole thing on the mass spectrometer, okay, which is used quite extensively in the mass spectrometer. In other words, it's kind of a cool little device, because actually you are going to shoot these molecules through a thing. And basically what it's telling radiologists, not radiologists, who are the gas passers? What do you call them in the medical field? Anesthesiologists and stuff. That's it. Okay. Y'all are going, gas passers? What are you talking about? Sorry. The anesthesiologists, okay, because they need to know, they have mass spectrometers on there because they need to know exactly how much of the knockout stuff you're getting compared to the oxygen that's in your head and everything else. Hey, in fact, for those of you who are going, I don't know about this whole 6-year medical school thing and malpractice insurance and all that stuff, we have a cool little master's in anesthesiology here at UMKC if you didn't know about it. And they make some pretty good skrill, and they don't have to worry about it. And it's a lot shorter. It's only a 2-year program. Okay. But anyway, and they're always in the operating room. You know. All right. But anyway, it used to be that they'd pay anesthesiologists a heck of a lot of money, but now that we've got all this fancy equipment due to physics and chemistry, it's not so much it's not such an art anymore. You know, So anyway, you got a mass spectrometer, and what happens is they shoot a particle through a parallel plate capacitor. Your favorite thing, I know it is. You just love it when I draw these parallel plate capacitors up here. Okay, so we got an E field going like this. All right, now I'm going to send an ion. So an ion, chemistry people, has what kind of charge? A positive charge. In other words, so this ion is going to be flying through here. So I've got this ion that's going to be flying through here. Now, what's it going to want to do? What's that ion going to want to do? It's got a positive charge. It hits this parallel plate capacitor. What's it going to do? It's going to want to curve down. So the reason we have this is so that it'll shoot that molecule straight. So what do I need to add to this thing? If the proton if this little molecule, positive charge molecule, wants to go down, what do I need to add to this machine here to make it go straight? To give it equal lift up so that it goes straight through? A magnetic field, right? So if I put a magnetic field in, if I insert this parallel plate capacitor, not a parallel plate capacitor, parallel plate capacitor in a uniform magnetic field that's going into the board. All right, so it's going into the board. Got this mess really right now, but in your book on page 665, it's got a cool picture that, or a better drawing. So anyway, going into the board, velocity is going that way. So which way is my force? My force by the magnetic field is going up. The electric field force is making it go down. I want those two to equal. In other words, I want QE to equal QVB. There we go. So based on the charge and its velocity, okay, all right, and so it's going to come shooting out of there with a certain velocity, and the velocity that I'm going to get, what up there cancels, didn't mean to shout at you, what up there cancels right away? The charge. So basically the electric field equals V times B. That's kind of cool. We're going to look at that later when we get to light waves, the intensity of light, and all that stuff. Because basically the electric field of a beam of light is going to equal the speed of light times the magnetic field that it's going through. So anyway, so that's kind of cool. All right, or of an electron. Okay, E equals CB in that case, speed of light. All right, so we've got this. Now, so therefore the velocity that this guy shoots out of there, the velocity, it kind of was bumping along, and then finally it hits here and it goes, oh, whoosh, goes flying through there. All right, and so the velocity that it goes through there is equal to E over B. But wait a minute. Sounds like I'm selling Ginsu knives again, right? Oh, by the way, I put that on your email, and I shouldn't have done that because some of the students that don't know me that well were actually wanting to know about the Ginsu knives. They're like, what, do we have to pay for it? They thought they were like clickers or something. They go, what are these Ginsu knives for $19.95 I have to buy now? I said, no. Everything's fine. Everything's fine. I was just being silly. You don't know about that TV commercial about the Ginsu. But wait, there's more. Now this is velocity. So now we also know this. We also know this, that E is equal to, now what did we say about the relationship between the charge or the voltage, the potential, and the electric field in a parallel plate capacitor? What did we say that was? You remember at all? Do you even care? No, just write it down. All right. Voltage over distance. It's the voltage, the potential, in other words, how much charge is up here and up here, the voltage, divided by the distance it's charged. So this is the voltage. All right? And so the velocity of this thing coming through there is equal to the voltage over B times D. That's kind of cool. See how you can interact all these things together? All right, now, okay, then the next stage that this little molecule goes through, the next thing that happens to it is it travels along and it's going to go through another little slit this time. Okay, it's going to go through another little slit. So we've given it a velocity. So this initial thing gave it a velocity, all right? And now it's going to come flying through this little slit here, and it's going to enter this uniform magnetic field, this B2 magnetic field. This one is B1. Okay? And this is a uniform magnetic field of B2. Which way is this magnetic field going? Out of the board. It's coming at you, right? And this guy is going like this. So which way is the force? So when this guy comes through here, which way is the force going to go? Down, right? It's going to go down. So he's going to come flying through here, and it's going to go down, and it's going to curve around, and bang, hit a detector right here. And it's this, and every time it hits that detector measures its mass, so we know what kind of molecule it is. Okay? Boom. So by using magnetic fields and all that, and so to find the mass of the thing, we know this, that F of C, which is mv squared over r, which we got the V is voltage over BD, equals Q VB2. Okay? So my V's cancel. So to find the mass of this thing, this is what I had you do on your quiz. So to find the mass of this thing would be Q B2 times R over V. Okay? But what did we say V was? It's this big V over BD, right? It's this big V over BD. So really what they do is they say the mass, they know that the mass of something would be Q times B1 times B2 times, I'm just going to write it down, times the distance between the plates over the voltage times R. There we go. Now that's in your book, but basically what I did was I took this guy and plugged him in here for V. Okay? Where this is voltage now. This is the voltage. And so, in other words, on that piece of equipment, we know it, if we're dealing with certain, if we're dealing with certain things, we'll know what the charge is. We know what the magnetic field is because we set them on both B1 and B2. We know the distance of that capacitor, and we know the voltage that we're charging that thing up to, and so we can find the mass. And that tells us what it is that's hitting it. Okay? All right. So you got an example in the book that says the mass of a molecule, and it's worded kind of funny, and it does something a little bit different. It says 1 electron is removed from a methane molecule. Okay? So 1 electron is removed, so that makes it an ion. So this molecule is going to go flying through there. They give you the velocity that it hits here, and you can work that example out on your own. That's example 19.3. All right, now, okay. So now, you've seen, okay, you've seen the, you've kind of seen the force on a charge. Let's take a look at this. What do you think would happen? And then we'll end with kind of a cool little problem. I kind of liked it. All right. What do you think would happen if we had a wire? We put a wire, okay, take a nice straight wire, put it through a magnetic field. Will it feel a force? Sure will, okay? The wire will definitely feel a force, okay? Because why? Oh, I'm sorry. I got to put a current through this wire, all right? Now it'll feel a force. Now it'll make sense to you. In other words, because what's current? That's just electrons moving, right? It's just electrons moving. And the energy of the current is close to the speed of light. But I think didn't you all do your lab already where you were trying to find drift velocity or something like that? Or you had a question on drift velocity? Have you done that yet? And nobody knew. They're going, what the heck? Right. But the drift velocity is really slow. It's only a few millimeters per second. Okay? All right. But the energy that goes through there is infinite. But anyway, here's the deal. If I've got a wire with a current going through it, and it's going through a magnetic field, especially if it has to be going perpendicular or the sine of it, the force is going to equal the amperage in the wire times the length of the wire times B times the sine of theta. And that, it's probably not obvious to you all because you're not used to this stuff. This is the first time you've seen a lot of this stuff, why that is. But if you think about it, if you think of Q, VB, you've got Q, what's V? That's velocity is equal to the length divided by the time, right? So I've got length over time times B. Well, if I just move that time underneath Q, there you go. What's Q? What's charge divided by time? Or the amount of charge per second? Yeah, it's amperage. So that's where that comes from. Okay? So, but the main thing you need to know is that the force on a wire is equal to ILB times the sine of theta. All right? And most of the time, I'm hoping that we'll be at 90 degrees. Okay? All right, so they've got this kind of funny little problem. I thought it was pretty cool. They said this. They said, all right, now think about this. Oh, by the way, the direction of the force is just the way you figured the other one too. All right, so in other words, you put now your thumb, which used to be the velocity of the electron, guess what that is? That's the direction of your current. Your thumb becomes the direction of your current. Your forefinger is your magnetic field, and then your salute finger is the direction, or that's why the textbooks all have just the hand, and then you stick it out like this. Okay, they don't want to, anyway, whatever, silly. It's like in education now, in math class, in the middle schools and the high schools, if you're throwing dice, you can't call them dice, you know what you have to call them? Number cubes. Can't say dice because there's the connotations of gambling, and that's good, you know, that could corrupt the young minds of the children. So you got to say number cubes. How many times do you think I said number cubes to my kids? None. All right. First of all, they're all little bangers anyway, so they already knew how to shoot craps. And they didn't, and I never knew, it was a cultural thing for me, I never knew that every time you rolled dice, you were supposed to snap your fingers. I'd never known that one before either. That was a new thing on me, too. It's like, oh, okay, I don't know how to snap my fingers. God, how wide are you from the burbs? But anyway, all right, now, off track. All right, let's get it back. Here we go. So anyway, here's a cool little problem. They said, hey, the Earth, we know that the Earth has a magnetic field, right? It's got a magnetic field. The magnetic field of the Earth isn't very strong. It's about 0.4 Gaussians. Do y'all know what a Gaussian is? It's 10 to the negative 3 Teslas, basically. So it's 0.4. So the actual magnetic field of the Earth is 4.0. So the magnetic field of the Earth is equal to 4.0 times, I misspoke, 4.0 times 10 to the negative 5th Teslas. A Gaussian is 10 to the negative 4th Teslas. Okay, Teslas. Yeah, it's the Tesla coil. Okay? And then I said, hey, let's take a, how long did they want our wire to be? Oh, let's take the length of the wire is going to be 1 meter. All right, length of the wire is going to be 1 meter. The mass of the wire is going to be, 3.0 times 10 to the negative 2 kilograms. And all you chemistry people are going, why can't you physicists use grams? You know, let's make it 30 grams. Sorry, 3.0 times 10 to the negative 2 kilograms. All right, and then we want to know if we lay this thing on the equator and how much current we can run through it. All right, let's say we're just going to lay it down, have it running along the equator. We're going to run some current through it. We're going to see if it levitates. How much current are we going to need to levitate this thing? All right, to raise up this wire. All right, it can be done. Here's what the picture looks like, basically. Okay, I'm going to try and draw it the best I can. Here's the Earth. Okay. All right, now, the Earth's, actually, this is supposed to be a sphere, okay, not CBS. But anyway, the Earth's magnetic field actually comes out of the South Pole, okay? It actually comes out of the South Pole, and then it curves around like this. So the magnetic field looks like this right here. That's why on your compass, when it points to magnetic north, remember, it's pointing in the direction of the magnetic field. All right? So the magnetic field is going this way. So if the magnetic field is going this way, and then I put my wire going along basically eastward like this, or as I said, it said, which way should you put your wire if you want it to go shooting out away from the Earth? Well, I said counterclockwise, and they said eastward. Well, I'm like, we're on a circle. How can you go east on a circle? You either got to go counterclockwise or clockwise. So I put counterclockwise. So my current is going this way. So if my current's going this way, the magnetic field's going up, then the force should be going out this way, opposing gravity. That's where we want it. How much current do I need for this thing to oppose gravity? So I just have this. It's pretty simple little equation. F equals ILB, which should equal mg. Because I want the sum of my forces to equal 0. All right? Because this is a 90-degree angle here. We've made this all. Okay? And so the amount of current that I'm going to need is I equals mg over LB. And B was really small. L isn't that big. M is really small, and G is that. And it comes out to be I equals 7.4 amps. That's a lot of current. That would kill you pretty quick. All right, so that's probably not a good way to go around. So we probably shouldn't just have a bunch of bare wires with 15 amps running through them floating around, all right, because people grab them. It could be bad news. All right. So it takes a lot of amps to fly through. But the main thing that they wanted to teach you there was F equals ILB. Okay, I'm not going to try and even go. Oh, wait. One last, since I brought it, one last demo, and then and it'll just take me a second when we talk about torque, because that's the next thing we're going to do. All right. So here's a nail with a magnet on it. Did you all do this for Weeblos on Wheels? Just show them this little motor. All right. You put that there. Now here's my voltage, okay? So this is going to push charge, right? It's going to, the charge is, and by convention, we're going to have the voltage, the charge going up, the magnetic field, well, actually the magnetic field's going up. I'm going to lay the charge on the outside of these magnets, which are also conductors, is going to be going this way. And so therefore the force is going to go in, and it should spin it. When I put it right on the side here, it should spin. Y'all can't see it. Here we go. One last try. Make sure you get this. This is for millions of viewers out there. This is going to replace Bill Nye, the science guy. All right. Here you go. Oh, yes. Oh, come on, work, please. There it goes. Yeah. There we go. And it gets going pretty fast. It also starts to get hot because of the current going through there. All right, so we'll talk about the torque and why that works on Friday, and then we'll do some homework problems.